Okay, so here's worksheet 2. We're going to go through the multiple choice first. It says a pulse. Now, a pulse is one full wave, but just one is sent down a string fixed at one end. Which of the following diagrams best represents a reflected pulse? Now, what happens here is it's coming in this way over here. This is actually an application of Newton's third law, because when the wave is, say, over there, like that, this point is going to be applying a force in the vertical direction on the wall. And the wall, by Newton's third law, will apply an equal and opposite force in the other direction. And so that force will be applied on the spring, on the string, and will tend to cause the wave to be vertically switched over, or a reflection in the horizontal line. So this line becomes switched over, and it also gets turned around. So in actual fact, this is the correct answer. So this part of the wave, let's say this part of the line reaches it first, and so this will be the first part to get reflected, and so head in the other direction, and there's this vertical flip, or this, I suppose you could call it a horizontal flip. Okay, so that's the answer for that. Looking at question 2, a plane wave approaches and passes through a boundary between two media. The speed of the waves in medium 1 is greater than in medium 2. Which of the following diagrams correctly shows the wave fronts? So what's going to happen is it's actually going to be this over here, because as you can see here, the speed of the wave has been slowed down in medium 2, and so these points on the edge over here that have been on this side over here, that have been in medium 2 longer, will lag behind these points over there, and so you'll get something like this. Sorry, my board is not very nicely synchronized. So you get that situation over there. This would be the case. This situation over here would be the case if the speed in medium 2 was faster than in medium 1. These two, because you've got these curved lines here, are not correct, because that would mean that in medium 2 you're getting a change in the speed, that it's not a constant speed in medium 2. So the answer is 2. Alright, question 3. It says the diagram shows the variation with distance x along a wave with its displacement d. The wave is traveling in the direction shown. So we've got the wave there. It says the period of the wave is t. Which of the following diagrams best show the displacement of the wave at t to the quarter t later? Now, our t is our period. So the t is the period, and one full period will give one full wave. So that would be that's the amount of wave that would move through in the period t. So a quarter would be a quarter of that. So in actual fact, you would get something like that. So if I continue the wave on this side here, you would have something like that. So that part there would have been shifted up, and so you would have this situation over here, b, because now this would be the correct one. I hope you can see that, because this part of the wave, if we extend the wave there, that part, that's one quarter of the wave, would have shifted up to that position over there, and so that one over there would be the correct one, would be b. Great, so let's go on to question 4. When a wave crosses a boundary between two media, which of the following properties of the wave does not change? Now, it's C. The frequency does not change when it's going from one media to another media. These things can change the wavelength, the velocity, the speed and amplitude, but the frequency does not change. Good. Looking at question 5, the variation with time of the separation displacement d of a point in a medium due to two waves is shown below. So we've got two waves, and each one is causing that situation there. Now we're going to need to just remember this because I've got to go down. I think the question continues over here. The waves are superimposed. Which of the following diagrams shows the variation with time t of the resultant displacement d at the point in the medium? So I'm going to actually do this one up here. So let's just go back here. So these two are superimposed. Now, if you have a look at this, this is 2a here. Let's just take this point on the wave. This is 2a, and this is 1a here. Now, you get an algebraic addition of the two. So you've got 2a in one direction, you've got 1a in the other direction. Your resultant wave will be in that direction. So you're going to get a resultant wave that's going to look something like this. It's going to be like that, and it's going to be like that. So going back to our answers, we can hopefully choose the correct answer for this, and this one will be A, as you can see there, A. Okay, going question 6. It says a graph shows the variation of the air pressure with distance along a wave as one at one given time. The arrows indicates the direction of travel of the wave. So we've got in this direction here. So it says the air pressure at point P is, now because the air pressure, because this part of the wave will be falling, if I took what the next part of the wave would be, as this wave a moment later, you would have something like this. I'm not a great drawer, so hopefully you'd get something like that. That wave is moving past, so P would now be down over there. That's where P would be. So P would obviously be going down. So for question 6, we've got that the pressure would be decreasing. It says light is incident on an air glass boundary as shown below. Which of the following is a correct statement of Snell's law? Alright, well, here we can actually use our data booklet. Here's our Snell's law there. And we have got, we are going to have N1 over N2 is equal to the sine of theta 1 over the sine of theta 2 over the sine of theta 1. That's what Snell's law is telling us. Now let's make this N1 here, and let's make that N2 here. So we're going to, if I put this in here, this is going to be this over here is going to be theta 1, and this is going to be theta 2. So if I just change my theta 2 here, I can, in my theta 1, theta 2 is S, and theta 1 is Q, like that. Now N1, because it's an air, would equal 1. So you get 1 over N2, N for the glass, is equal to the sine of S over the sine of Q. So it's really important just to make sure that you identify, just put in your values here and then make sure that these correspond, and then just work with the formula. Okay, so let's see which one works here. This one over here, the sine of P, we're definitely not dealing with P and R, so anything with P and R won't work. We're dealing with Q and S, so we need Q and S. So actually it can only really be this one over here, because it's always that one, so it's going to be D. So that was pretty straightforward. You didn't even really need to work with that. But let's just say this. So the sine of Q is equal to, so this constant N, It's a constant times the sine of s, and that's that one over there. Fine, going on to 8. 8 is pretty straightforward. It's going to be A. When you get this wave over here, by what we call Huygens principle, each point of the wave is a source of new waves. So this point over here, and because it's got no points over here on the other side producing wave, these waves over here on the side are not cancelled out. So you actually get the idea of diffraction, the bending of waves around a barrier. And going on to question 9, it says a transverse traveling wave has an amplitude of a0 and a length and a wavelength of lambda. The distance between a crest and its neighboring trough measured in the direction of energy transfer of the wave is equal to. So we've got a wave like, it's a transverse wave, so it's a wave like this where the particles are moving to and fro, up and down there, but the energy is moving in this direction. So the distance between a crest and a neighboring trough in the direction of, so this distance over here would obviously be half a wavelength, or the wavelength over 2. So the answer for that one would be C. Okay. I'm going to leave question 10. I'm not going to, I think you can leave that question out. It seemed to me to be quite ambiguous. Thank you very much.